So the other topic for today is then data reclassification. So you can have some kind of threshold values or ranges as conditions, and based on that, or based on then some further spatial condition, you can then assign a binary value that is suitable or unsuitable, or then you can classify values into ranges. Or then if it's qualitative data, then you can reclassify, let's say, land cover classes to more coarse land cover classes. So we're talking about map plottings next week, but I brought a few books with me which talk about map classification. So if you haven't taken many GIS courses, so for example here, you can come and browse these afterwards. But for example in here, there's quite nice, these are not super new, but there's discussion about the suitable number of classes, and there's really no right or wrong answer to the correct classification scheme or the correct number of classes, but there are some rules of thumb. For example, if you're making more than 6 classes, you should have a good reason for that, because the human eye might not capture so many classes. And then if you have less classes, then you get kind of more clear or distinct patterns, and then if you have more classes, you have more complicated patterns. So if talking about making maps, you always need to think what are you making the map for, what is the message, what is the audience, and so on. So nowadays it's quite easy to make a quick and dirty map just by pressing some buttons in some web mapping application, but of course us as GI scientists or geographers should then pay a bit more attention to, first of all, the classification, and then of course the colors and so on. But today we'll indeed talk about classifications. Was there something else useful? Yeah, and indeed, like today we'll start with choropleth maps. So they are thematic maps that represent some kind of data. Often if it's quantitative data, then it's being classified into ranges. So we are now dealing with the classification today. For doing it, we are using Pysal, mapclassify, which has implemented these common classifiers, and you can also then define your own classifiers. So we'll look into that in more detail. So we'll first look at these kind of common classifiers from the Pysal module, and then finally learn how to define our own function with our own threshold values to classify the data. And as input data, we'll use the same travel time matrix data, and hopefully you managed to store the GeoJSON file. If you don't have it, you can also use the original shapefile, then it's just a bit bigger. Okay, so I think, at least if you have studied geography, we learn these or do some kind of thematic maps already in the first year. I shared some notes with myself. There are some quite nice materials. Let's check this one. This is unfortunately now only in Finnish. Some of these Statistics Finland's materials are in English as well, but for example here, it's a visualization of people with a higher education degree. So the data is exactly the same, but there's a different classification scheme. So the maps look quite different. So there's same amount of classes, but then there's some kind of a different way in which the values have been divided into ranges, and thus the maps. I don't know if they tell a different story. Maybe then, if you think that the high values are the dark ones, so then this is maybe a bit more equal compared to this one where you can see the city regions and such. Didn't look at this so carefully. And then always when you're classifying quantitative data, you should somehow have a look at the distribution of the data. So we'll be plotting some histograms, so the frequencies of values. So there's always the value. For example, this could be 1, 50, and 100, and then in this normal distribution, most of the data, so this is the number of observations with that particular value, so the frequency is then plotted. So often when working with real data, the distribution is not so normal. Maybe more often there's many low values and then only a few high observations and so on. And then also there's no right answer that what distribution matches with which classification scheme, but then there are some that are better suited than others. So those Finnish speakers, I recommend that you go through. This is a bit like repetition from bachelor studies, but this luokittelumenetelmän valinta section is quite nice. It goes through in Finnish these different classification schemes, quantiles, equal interval, natural breaks, I think, as well, and so on. So based on the histogram, the data is divided into ranges. That's what we are doing when classifying data. What is this? So I'll maybe go back here. So in the Pysal mapclassify module, I'll see if this actually opens. Not yet. GitHub. Anyway, so in this module, there are different kind of standard classification schemes available, and we'll have a look at some of these a bit more detailed. So quantiles, often you kind of divide, you need to decide the number of classes, for example 5, and then quantiles divide the data into kind of equally sized blocks. While then natural breaks kind of tries to look for natural gaps in the data and puts the threshold values there. Yep, so let's start with this for a while and then have a break when people start falling asleep. So under lesson 4, somewhere in the middle of all this data, there's a reclassify notebook. In there, and if depending on the file name you used, should be this one, we can start by reading in the data. There we go. So GPD read file path. I'll store that. Well, I'll use the same variables as in the materials. So read in the file, and there are no data values in this matrix data. They are stored with -1. In the exercise you'll do this a bit different, but here I'll just kind of filter them out. So I will use this column for public transport travel times, PTR, TT, and recognize all the rows where that value is equal or greater to 0. So excluding the no data values. That's the condition, and then using lock. So put all the condition inside the lock indexer and store that in a variable. That's now a bit maybe tricky syntax, but I hope you managed to copy it. So it's the same input data as before. There's all these different travel time values and distances. And this one here, we make a kind of true false series, identifying the rows where there are not no data values, and select all of those. I think we'll do so. I'll now then show, so this is kind of the thing you would normally do. So when plotting data, just run that first. So this is the same thing we did previously. It plots all the geometries with some default color. But when plotting data, we can also define, it was this PTRT, TT, so we can define based on which we want to color, kind of give a thematic color to the grids. So there's some default, might be natural breaks. Let's see soon what is the default classification scheme when plotting data. So now this is a visualization based on values in this column. I assume that the more blue, the smaller the value, because this is travel times to railway station, and then the more green, the higher the value, so the longer the travel time. But we can then actually define the classification scheme by passing this scheme parameter. Now let's check. I think it's actually like this. No. Natural breaks. So they have just changed this syntax. So natural breaks, all lowercase. In the scheme parameter, so this scheme parameter already uses the Pysal mapclassify package in the background. So we'll have a closer look at that package after the break, I think. But there's now some kind of a classification, some kind of transformation from the values to ranges based on this natural breaks classification approach. And there's now, I would say, 1, 2, 3, 4, probably 5 classes. As we are kind of dealing with this continuous travel time data, even though it's good to avoid high number of classes, we can try how it looks if we increase the number, so to make more kind of this smooth transition between the colors. So with the K parameter that defines the number of classes, we can change the color map. This is now, so I'm typing in capital R, D, capital Y, L, capital B, U, which is kind of a standard color map scheme from Matplotlib. There we go. I think there's no lines, but we can also add line width. Remove the lines, so in case there was some border lines in the grid polygons. And then finally add the legend. So this actually shows the class values. It's now a bit in an ugly way plotted on top there. But already like this, using the GeoPandas plot, we can somehow influence the way in which the values are defined. So now the more red the value, the closer by public transport to the railway station. So you can see these, there's train stations popping up as kind of hotspots and so on in the region. Maybe. Yeah, let's do so. Let's skip this walking distance thing. So basically you could just change the column, plot the map again, get a bit of different output, but I'll just explain quickly this map classifiers, and then we'll break for 15 or 20 minutes. So what we are actually then using on the background is this mapclassify package, and what the documentation that I wanted to show you looks like. So as you see, there's documentations in different places, but this GitHub repository from Pysal mapclassify is quite good. So it lists, shows how to use all these different classification schemes using the mapclassify package. So there's all these familiar sounding classification schemes listed in here. So let's see a bit what happens and how we can then start modifying the data or controlling this classification scheme in a bit more advanced way. So for that we need to import mapclassify. If you're working on your own computer, you need to install it. So we'll do that after the break. So if we now would then want to initiate a natural breaks classifier, we need to call mapclassify Then now they changed the syntax. I think it's natural breaks. Now you can see this camel case naming. I think that's correct. And then if we check the documentation, so mapclassify natural breaks, I'll zoom in. It takes 2 parameters, so there is a y, which refers to the values being classified. So the classification is always a function of some value range, and then k is the number of classes. So when we apply this to a data frame, the y is then all those values from one column. So then in here, we could give that y equals to, we have this ACC data frame, and then PT are TT column, so travel times by public transport in rush hour. So by default there was 5 classes, and as we did previously, we increased the number of classes to 9. So then we can see actually what is the classification scheme that then influences how the map influences the values, how they are divided into classes or these ranges, and then finally the map output. And then it gives us a bit more information, count of the values in all of these classes. There's the kind of lower and upper bound, so this is now 20, and then 3 decimal places. So then the highest class, which is then over 115 minutes, so quite far, probably somewhere in Nuuksio. So there's only 3 grid squares in that class. Yep, and we could do the same thing for quantiles. I'll just jump to here. So if we, I'll copy that one. You can continue in the same place. So if I save now this kind of the template for doing the classification into a variable like that, so I can then print, so it's the same object, but then for example I can get the bins. So bins refer to these threshold values. So classifier.bins returns to me a NumPy array with all these threshold values. So I think, well, yeah, let's still apply it and then have the break. So I'll again copy paste this, but this is now in no way linked to the original data frame. So if I want to apply the classifier on the data frame values, I need to make the classifier, and then I don't give any values. I can give the number of classes if I want, and then make. So this kind of creates a function that would then apply this classifier on any data, and I can store that into a variable. So now I have a function definition stored in this classifier. And then finally, if I have some column out of the original data frame, RTT, then we have learned how to apply functions. So then I apply the classifier, and then I get as an output the kind of classification for all those values. So now if I would change this back to 5 and run this again, so then the maximum value here would be 5, because then we're making, or is it then 6? Only so many classes. So we create the classifier and then we apply the classifier. But I suggest that we now, with this knowledge, we could have a break, and after the break, still before installing stuff, we could then apply the classifier on the map data and plot it. So sometimes it's useful to get the actual classification values also stored as an attribute. And then we'll spend a moment plotting histograms. So as I mentioned, the classification is based on the distribution of the values, and we can then also plot the classification breakpoints on top of the histogram, just to understand where are actually the breakpoints and how many values each class have. But I'll show this, maybe takes 15 more minutes after the break. So let's say so that we continue at 5 to 6 in the other class. So there's still 5 minutes time to go to the cafe. Continue a bit. So let's wrap up the classification stuff, and then I'll show how I often install the Conda packages. Then after this, if you want to stay for that. But so far we checked how we can kind of on the fly classify data when plotting maps. So using the scheme parameter, you need to have the mapclassify installed, so Pysal tools to make the classification on the map. So some breakpoints based on the data distribution. And now before the break we checked how we can then kind of dive deeper into the map classes, create these classifiers, actually check the bins, the threshold values, how the data gets distributed into these bins. And finally, if we then kind of separate the process, so we first create the classifier, and then so with this mapclassify classifier name make, so this just makes the function, and then we can apply it. So this applies it on the whole column. So that's where we stopped. I'll hope my instance is still alive. Let's do so. There, and if I would check, so this is indeed, I'm taking the column. I could also take a set of columns, so apply the classifier on multiple columns. So what I get out from this syntax is a pandas data frame. I need to open my notes. As an output. So of course we would then, if we do this in pieces, we would want to apply the classifier on a column and then plot the data based on those classified values. So then I'll sneak peek from here which column name I use. So we are now working with the ACC data frame. And there's some set of columns. I'll just show you, don't have to do this necessarily. So there are the original columns that are in this data product. So I could add then, add a new column. So I now called it NB, so natural breaks, then public transport, rush hour, travel time. Column name equals to, then I'll copy paste this piece of code where we have the data frame, select one or several columns from there and apply the classifier that we defined here. So we have made this function and then we apply the function in there. So we can then check, if I check the head of only that column, and I could also then add, leave this here in a bit, so I have the original values. Oops, I need to have them in a list. Sorry. So on the left side there is the original values, so these are quite high numbers, they are minutes, so 99 minutes, that falls into one of the kind of higher end classes. We can then check tail. So then there's some 70 minutes. It falls into class number 6 now that we created 9 classes. So in some cases you can just do the classification while plotting. For some other applications you might want to store the classification as a new attribute in the data frame. There we go. Right. And then based on that information, I'll just store that in a column in there. So now we have a new column in this data frame, and we can plot it again. Test that it works. Now using this new column as the attribute, so NB PTRTT. Legend true. So then we get an output with then these the classified values in there, and with a bit different legend also. So it's basically, then of course we could give the color scheme and whatnot as we did previously. So it doesn't then matter if you would do it past the parameter scheme, natural breaks, K, and so forth, but for some intermediate processing you might then want to have the values also in a column as a static representation of the classes. But then this is something I added to the materials since last year. So to further understand what happens, it's good to always inspect the histogram of the data, especially with quantitative data. So with pandas, there is a pandas series, pandas data frames. There's a function called plot.hist, and we can just plot, as we're interested in one of the columns, we can directly plot the histogram for that. So the original values PT are TT. So it visualizes a histogram. So on the x-axis there are the values that you remember, there are travel times in minutes. So 0, that would be at or close to the destination grid square. Then most of the values are somewhere around 40 minutes. So there's so many grid squares with value 40, and then there's not so many grid squares with high values. So the frequency and then the actual value. And to make this more nice, we can add a bit of groups in there. So if you add increase bins, so then you get a bit nicer looking or more detailed histogram. So column.plot.hist and bins. And then here we can combine the histogram with the classes. So as before, let's make some classifier, which was mapclassify dot natural breaks here. And then we have, now I want to actually get the bin values from there, so I won't make the classifier, I will just kind of already classify the values. So the Y is then the same column, I'll just copy it from here. So the PTRTT column, so all the values as a series, and then you can give the K value in there. And as you remember now, we have, if we do this classifier, if we do classifier dot bins, just put it down here, so I can get the class values. Then we can plot the histogram. You can copy the previous code from here. Plotting the histogram, and then our task would be to plot the class breakpoints on top of the histogram. And in matplotlib, you can plot whatever you like on top of the plot. So we have already imported matplotlib pyplot as PLT. So we could do PLT dot, there's this AXV lines, so vertical lines like this. And then the first parameter in there is value. I didn't actually try this, but we could, for example, of course, check if we can plot the mean value. So where is the mean value? Sorry. It's like this. Yes, okay. Demo effect, which wasn't a demo effect. So then we have a line now, but it's blue, so we can't see it. So color K would make it black. So just like that, we give a value. So value is the mean value of all these travel time values, and then we take the mean, which is somewhere, it's 40, let's say 42, and then we tell to matplotlib to plot a vertical line at 42. So this is now the mean value of the data, and if you're doing, I don't know, you're doing your master's thesis, might be useful to create this kind of a plot. So already with this descriptive statistics, mean, standard deviation and such, you can tell something about the distribution, but of course then the histogram gives you a visual idea. Is it normally distributed, if it's skewed and such? So this V line indeed creates a vertical line at certain value, but now we would want to draw a vertical line for each of these threshold values. So how to do that? In English, for each line, print a vertical line. So we'll make a for loop around the plotting. So for line in classifier bins, PLT plot vertical line at value line. Oh, sorry, maybe this is value is a better variable name. So for value in bins, so bins are the threshold values, plot to the existing figure, plot the vertical line, looks something like that, and then line style equals to dashed, oops, dashed. That's already a bit nicer, and then you can decrease the line width. So this is now, should make it super clear what happens when we're creating natural breaks for this column values. So the first class is quite wide, then there's more data, so then there's less range, and then again the biggest class covers quite a lot of values. And now that we have this, we could just modify the code. Maybe I'll actually, copy the whole thing. And I think we have a slot for quantiles, for example. So then there's mapclassify.quantiles. We could make it the default 5. And that's enough. So then a quantile classification with 5 classes would produce something like this. Then you can increase the K, get more values. So with this, you can then assess, is it then reasonable to have all these large values in the same class? It might be, because over 60 minutes is already, like, that's a long time to sit on a bus. So in that way, you again need to think about the output map and what does it make sense to have then class breaks with values greater than 1 hour. Maybe it's not interesting, is it 1 hour or 1 hour and 15 minutes anymore, but then 15 minutes and 30 minutes, there you want to have more breaks. And in the exercise you will need to use, there are these predefined classes, and then there is this kind of user-defined classes where you can then self pass the bins. So in the exercise you want to make a map where you have 5, 10, 15, so 5-minute interval map, so that then we can compare the travel times between different destinations and between different travel modes more easily. Yep. So if you have time, do experiment, and you could of course try to then, if you plot this histogram, you could make a 2-panel plot where you have the histogram of the classification scheme and then the classified map next to each other. So that would be quite nice. And also as an idea for the final exercise, if you're dealing, for example, with this dataset or any other numerical data, good to plot the histogram, and then if you're making a map, visualize the class thresholds also on the histogram. So, or you can even make 2 different options and discuss the message of those 2 maps. But I'll quickly show then a bit more complicated example if we would want to do kind of multi-criteria analysis. So as I mentioned in the beginning, we could, for example, want to look at regions where travel time is greater than, let's say, what are we giving in here, but it could be greater than 20 minutes, so assuming that it's not the most expensive areas, but still less than 40 minutes, so that we don't spend the whole day sitting on a car or in a bus. So what happens in here is that we're defining a function which we will eventually apply on each row of the data. So on the travel time matrix, then we define some source columns. There's a threshold value, 2 options for that, and then a definition on which column we are storing the output. And when we are applying the functions on DataFrame rows, we can then access the columns like this. So we could define that, for example, public transport travel time should be less than threshold 1, and public transport travel time should be greater than something else. And then if the conditions are met, then we give 1, and if the conditions are not met, we give a 0. So as an output, we get a binary classification on this. And you could then, for example, build a tool where the user can set the threshold values, and then the output gets visualized based on this. But we'll just quickly see how we can then apply such a function on our data frame. So we have the data frame and .apply function name. So we had this custom classifier. And again, often if just using defined functions, you need to run this. It's often quite useful just to copy the parameter names, paste them here, so then you remember which ones you need to define. So we could use the travel time by public transport as the first source column. Then another condition could be then based on walking. Threshold for the public transport is can be 20. You can put some other value. Then walking distance, those are in meters, so then there's some distance threshold for that one, and then the output we want to store it in a new column. And in this example, actually, we need to define the column before we apply this. So can just make an empty slot for the output as the function is defined, so that we need to give the output column name in when calling the function. I'll do like this so we can see everything. And then again, we want to apply it column-wise. So So I'll maybe do like this. So I'll check what we have now in the suitable area. Let's see, a bit more values. So at least many of the values in the beginning are 0, but the travel time matrix is constructed so that these are probably at the edges of the area. So quite a few grid squares have ended up in here. And then finally I'll just show how it looks like if yeah, well, that's maybe useful. So if you have a column like this and you really can't see what are the values, so there should be only zeros and ones. So you can always check the value counts. So indeed there are 2 values and there are only 9 grid squares which then met these criteria. And we can also plot them. And now that we have learned to plot things based on a column value, we can then see that then there's, based on these criteria, then there's some in Herttoniemi and along kind of northeast direction from the city center that met these two specific criteria. So then you can test some other criteria, make a more sophisticated location multi-criteria analysis in there. So this went a bit quickly, but you can inspect this code a bit more, and you could even add some more conditions. And here indeed we are only making this binary yes or no condition. So in this week's exercise, I hope the links already work. Show it from here. So we kind of have, well, there's 2 compulsory problems, and then we added, if you do problem 3, you can gain 5 points, which you can overall compensate for missing points. It's just that it's quite a laborious package, but this last exercise is quite nice as well. So in the problem 1, you need to do some attribute joins. So we have the grid data set, and you join accessibility data to different shopping centers and visualize them using a classifier. So just what we did. Then in the second problem, we calculate dominance area. So here the idea is that you need to check across the whole region for each location what is the closest shopping center based on the travel time matrices. So there we have several shopping centers as input, and then in the final problem you should then join the dominance areas with population data and then report kind of the catchment area with population information for each shopping center. So assuming that people would go to the closest shopping center based on travel time, of course there's different reasons why we choose to go to different locations. Then this is kind of a market area analysis, that how many people live under the influence area of each shopping center. I'll quickly show the output. So from the first one you'll create something like this. So 2 maps for Itäkeskus, ITIS, 2 maps for Myyrmanni. So the idea is that you first develop the process for ITIS, then you repeat it for Myyrmanni, and furthermore, this is an optional thing, you can create a process which automatically plots everything into a 4-panel plot. That's quite a nice task, but this is already enough. Then in problem 2, this is what we mean by dominance area. So there are 7 shopping centers. You need to read in the data for all of them, combine them, and then for each location check which is the closest shopping center. So all the data is there already. You need to just kind of fetch this result from the data. And then this one shows from each location the travel time to the closest shopping center. So it's not anymore like distance to one location, but to distance to the closest facility. So then you could think applying this to sports facilities or hospitals or such. So the basic problem then can be applied to different application cases, but here as input we have the travel time matrix for 7 different shopping centers. Yep. And then the final problem, which is optional, so don't get overwhelmed if you don't have time to do this, but there's kind of minimal instructions, but your idea is then to join the dominance area information with population data. You can design it freely and then report the population within each dominance region. For public transport, then extra bonus if you want to do it for a car, but that's already kind of too much. So if you get super excited about this topic, you can then like save some of the good stuff and make the final assignment based on this data set as well. So all of this then feeds into the final assignment there. You could further automate these steps if you choose to work with the travel time data. And there are quite good hints on the hints page.